Hello, Emma.
It's fine. Just wait.
Hi, everybody. Okay, so we already talked about, so we have done 3 chapters. The first chapter talked about some basic stuff, the errors and stuff. Then the chapter 2 and 3 are about the kinematics, which is only involve problem of motion without considering any forces. So from chapter 4, we are going to dynamics. Dynamics means we are need to consider forces, and because forces is the reason why we have the acceleration, right? So in chapter 2 and 3, there's no forces. We know there's acceleration, but we don't know what caused it. So before I start, any of you have any question you want to ask? Like maybe homework problems or anything you want to ask about the previous 3 chapters? So yeah, I was trying to collect some feedbacks or questions from you guys. So maybe every time you submit your homework, try to also ask 1 question about anything you want, okay? So at least in this way, we can have some communication and interactions. So all right. So the first thing I want to talk about in this chapter is the forces, right? In physics, right now we know 4 basic forces. So there are gravitational force, electromagnetic force, there's strong nuclear force and weak nuclear force. So the last 2 are like inside the nuclei. So we are not going to talk about them. Then we have this gravitational force. Everybody knows what it is, right? We are attracted to the Earth by the gravitational force. So we are not going to falling into the sky or the space. Electromagnetic force is the force between charges. The thing is, who will tell me normally what we said, I push you or I pull a string, which category it belongs to that force? So if I push on the wall, right, there's a force I apply on the wall. So which category it belongs to? Does that belong to the gravitational force? Or is the electromagnetic force? Or is the strong or weak force? Anyone? So the normal way when we talk about the force, the everyday force is actually everyday force, like push, pull. They are belonging to the EM force. Why is that so? Because we need to think about in a molecular level, right? If there's a wall, for example, there's a wall, and you push your hand on it. So then assume this is your hand. So why we have a force on the wall, and the wall also have a reaction force on the, if you push the wall will feel a force, and the hand will feel a reaction force. Because if you are thinking about they're in the molecular level, this molecule is trying to compress this molecule, and this molecule will react on this molecule. So why the molecule, how the molecule keep their shape is because the EM force, the electromagnetic force, because there's a electron circling around the molecule and there's a nucleus in the center. So the force between the electron and the nucleus is that whatever is what keep the shape of the molecule. So the everyday force is actually belonging to this category, right? So gravitational force is basically found, we can say it's found by Isaac Newton, right? It's a universal force between anything and another thing. So as long as they have mass, they will have an attractive force called gravitational force. All right, we're not going to talk about the strong and weak force. So basically, in this book, we only involve, in this class, we only involve these first two forces. But in a macro view, the electromagnetic force will have a lot of different forms we can recognize. Okay. Now let's go to the Newton's laws. Newton has 3 laws, right? The first law is about inertia. So who can tell me what is Newton's first law? You'll learn that, right?
An object that's in motion stays in motion.
Yes. The objects stay still or in a constant move if they are not disturbed, basically, if there's no force working on it. So the Newton's first law is tell you of something will stay here or moving with a constant velocity, right? These are 2 status they want to stay. This basically, the case 1 is actually a special case of 2, right? Because when it's not moving, it's basically called constant velocity of 0. So what this property, we call it inertia, but this is very simple property, but you know, at the 1,000 years ago, 1,000 years ago, it's actually not easy to recognize this property, because when you put something like Aristotle's found, if you have a block, if you push it, it will move. If you don't push it, it will not move. That's why in physics, we are trying to get rid of all the disturb, you know, get rid of the unideal environment. Like if we have a box on a frictionless surface, then if you push it, it will keep moving, right? So it's also like, if we think about another experiment, there's a people dropping a ball and a feather together, right? So which one will drop to the ground first? Of course, the ball will go touch the ground first, and the feather will drop to the ground slowly. Then people will have that one conclusion of heavy object will fall faster than the light object. But if we put them in a vacuum room, then you can see these 2 will drop exactly at they will drop at the same speed and reach the ground at the same time. So in physics, we need to find a law or the intrinsic law to we have to get rid of the disturbance, basically, the environment. We have to find out what is really, control the object. It's not, we need to get rid of the friction here. We need to get rid of the, the air friction. So when we get rid of all these things, we can think about this object is in space and no forces on it. It will either be moving with constant velocity or not move at all. Right? If you don't apply a force on it, it will keep its original status. So we call this inertia. So it's called the law of inertia. That means you want to keep their original status. So is this law, is Newton's first law always obeyed? Do we need to have some condition? So what is the condition for the Newton's first law?
No friction.
Acceleration.
No, because friction or force is originally talk about when no force is acting on this object, right? It keeps its original status. So the condition is about reference frame. Think about if you are using an accelerating car, or if this train is accelerating with the acceleration of A, will an object on the train still obey this first law? It will not. I mean, if you use the train as a reference frame, if the ground is frictionless, this object will accelerate to the back of the train, right? So for an observer in the train, he will use the train as a reference frame. And he will observe this thing is moving and accelerating without any force applying to it, because nothing is working on this thing. So we call the condition for first law, we need a inertial reference frame. So inertial reference frame, it means this reference frame is not accelerating. So it has no acceleration. This reference frame itself has an acceleration of 0. So actually, we use Earth as our reference frame, and Earth actually is not an inertial reference frame. But because the acceleration is it's very small, most time it doesn't affect our experiment. So we still use Earth most of the time as a reference frame. But ideally, Earth, because Earth is turning, right? Earth is turning around, so the thing on the surface of the Earth will have acceleration. So we'll talk about that more later in this course. All right. So the first law is called the law of inertia, and the condition is inertial reference frame. Okay. So now, what is the mass? So usually we see, if it's hard to get a definition of mass, right? You cannot say it's bigger or smaller or denser or something. So what's the way we measure a mass? Basically, mass is something we call is how hard to change the status of an object, basically. So for example, you have something here, you have another thing here. How do we know this bigger thing, if this bigger thing has more mass or less mass than this small thing? So what we do is we have to apply a force on both. So if it's harder for this bigger one to change to gain speed and easier for this small one to gain speed, then we know this will have bigger mass if small acceleration. So basically, this is the second law. But before we talk about second law, this is how we talk about it. The mass is how hard to change the status. So about the mass, there's actually two concepts. One is called inertial mass. The other is called gravitational mass. So this comes from different, so how do we, when do we know we are measuring an inertial mass? When do we know we are measuring a gravitational mass? Basically, a simple way is you check if there is gravity involved. So basically, for inertial mass is, okay, you have a mass, you apply a force. So the mass, and then you measure A, right? So the mass is some force divided by the acceleration. So inertial mass is basically how hard for a known, this is a known force, how hard a known force can change the acceleration, can change the velocity of the mass. And gravitational mass is actually a different thing, because from the universal gravitational law, any two objects, M1 and M2, they will have an attraction force between each other, right? So we have this, we'll talk about this later, but I'll write it down here. The attraction force is some factor times M1 times M2, then divided by the distance of the center of the mass. So here to here. So here the mass is called gravitational mass. So basically we can say if we know a gravitational field, gravitational field. So how do you represent what property a gravitational field has? That acceleration on Earth's surface is the G, the gravitational G. Then if you have a mass, you will have a force. So here, the difference is here. You measure, you have a known field, gravitational field. Then for some property of mass, you can measure this force. So if you look at the difference here, you have a known force, then you measure your acceleration, this is inertial mass. But if you know a gravitational field and you measure the force, what you find is the gravitational mass. So this actually are two different concepts, but currently at this stage, we haven't found the difference between these two mass. So they are, most of the time we're just call mass. We're not distinct them. You know, so now if people ask you, what you measured is a gravitational mass or a inertial mass, you'll see if you use the gravitational force here. So for example, if you use a spring, right? The spring, then you drag the spring to the left because the spring shows how much the force is. Then you measure the acceleration. You find the mass from this experiment. What mass you are measuring?
Inertial mass?
Yes, because you are using a known force divided by the acceleration. So you find inertial mass. Another one is you are using a scale, right? You put, if you put a known mass here, right? And you find another unknown mass on Earth. Then, for example, you can find this mass by the distance of the mass to the pivot point, right? So what kind of mass you are finding in this experiment?
Gravitational mass?
This is actually gravitational mass because you are using the gravity to help you do the measurement, right? You're not using a known force. All right. So this is just a concept, and it's not actually. I mean, it's a. You can think about the difference, right? They are actually a different definition of a mass. All right. Next, we'll talk about the second law. Second law, you know, today I was writing this note, and my son, he's 7 years old. I said, "Oh, I learned this second law of Newton's second law at school." So, okay, so you should have heard of this when you were like first or second grade, but you know, most people may not understand what the true meaning of this Newton's second law. All right, so Newton's second law, let's say, so let's write it here. So what is this symbol means? What is this big sigma means, right? In math, we call it the summation, right? So basically, it's the summation of all the forces and its vectors equal to the mass times acceleration of this object. So first of all, we're talking about one object. Okay. Second of all forces need to act on this object. Three, the acceleration is the resulting acceleration of all the forces. Okay, so basically, right now, if we talk about one object and you have multiple forces acting on it, right? F1, F2, F3. So first of all, you need to find a summation of the force. So the summation of force is because the force is a vector, right? They're all acting on this object. We assume they are all acting on the center of mass. So we use a vector addition. So this is the sum of the F1 and F2. Then we use this and that, right? So this will be the summation of all the vector forces. So if the vector force have this direction, what will be the direction of acceleration?
The same direction as the net force.
Right, because here we can see this is a scalar. A scalar is only going to change the magnitude of something, a vector. It's not going to change the direction. And the mass is always positive, so it won't change it into a different direction or the opposite direction. So yeah, it's actually, that's it. That's how what the Newton's second law is. But when we use the Newton's second law to solve problems, we need to remember these 2 points. So there's one saying is like, there's one person is talking about, okay, this person is trying to drag this. Now this is, let's wait. Let's talk about Newton's third law first before we go to this example, okay? So Newton's second law is called, the forces comes in pairs. So within 2 objects. So the important thing is there's 2 objects. So the force must have a source and the target. There's no force that is like, okay, there's a force, and I don't know where it comes from. So it must come from something. So the force must be exerted on one object by another object. So you have to, when you find a force, you always need to identify another object. If you cannot identify the other object, that means that force may not exist. So here's the question here. For non-contact force, what is the other object? What is the non-contact force? So you have a ball in the air. There will be a gravity, right? Gravity is mg. So this is the force. So there's a force mg. So who can tell me what is the 2 objects involved in this gravity force? We need to identify 2 objects. So the ball is the object the force is acting on. So we call this a target, the target of the force. The ball, right? So where's the source of the ball? Source. When this force is gravity, when we are talking about gravity. The gravity is the kind of force I call non-contact force. So that means it's not as obvious as there's a box and there's another box and they touch each other. This one gives the one give 2 a force to the right, the 2 give 1 a force to the left, and because they have a contact, right? So for the non-contact force, what is the source object? Anyone?
Usually it's Earth.
Yes, that's the Earth. We can draw a big thing here, Earth. So gravity, because this gravity is, so when we talk about non-contact force, so we are talking about a field, an object in the field. For example, if this is the electromagnetic field, if this is electric field, right? This is electric field line, and then if you have a positive charged particle in the field, it will feel a force. So who can tell me the force direction for this one? This is the electric field line. So you may not know the direction of a field, electric field line means, but the field line go from positive to negative. So in this case, it's easy to see. If the positive is on the top, negative is on the bottom, this one will be repelled by the positive and attracted by the negative, so the force will be going down, right? So for gravity, it's the same thing. In the gravitational field, you have an object with mass, then you will feel a force go along the direction of the field at mg. So for this case, the Earth, which is also the source of the field for non-contact force, right? Okay, for non-contact. That's the way you find the object. Okay, the source of the field. So for example, we know the positive charge and negative charge, right? They attract each other. So this one have a force go that, this one have a force go that way. That's because the negative charge will generate electric field like this. And the positive charge also generates an electric field like that. So the positive charge is in the field generated by this negative charge, and the negative charge is in the field generated by the positive charge. Because they are non-contact, but you have to find the source of the field, then you can find the source of the two objects, because every force have a source and target. So that's how you identify these two objects. So now, remember, when we talk about Newton's third law, we call there's the action and there's the reaction, right? So action, if we have a target, we have a source, and we have a target. Object 1, object 2. So for action is the source acting on the target, then for the reaction, it will be the target acting on the source. So now, who can tell me the reaction force of this gravity? What the direction and what is the magnitude for the reaction force of this gravity force? I mean, the pair, right? When we talk about Newton's third law, we're talking about a pair of force. If one is gravity, the other one should be, they have to be in the same kind of force, right? If one is gravity, the other one should be gravity also. And if this one is going down, the other one is supposed to be going up. And the action and reaction will have the same amount of magnitude. So, anyone can tell me what is the reaction force for the gravity of this ball?
It's also mg. It's going up.
So which object is acting on?
Like the ball goes down and the earth goes up a little.
Right. So it will, because this action force acting on the ball, right? Sorry. The action force acting on the ball, then the reaction force will acting on the source, which is the Earth. So it's the Earth getting gravitational attraction from the ball, and it's also in the magnitude of mg. Okay, so that's so the rule is you need to identify two objects, then you have action, right? You identify two object, source and target. Then reaction, the source become target, the target becomes source. That's simple. Then what else? They must be the same kind of force, okay? So if one is a gravitational force, the other one cannot be an electromagnetic force. All right. So let's see the notes. For non-contact force, we track the source as the source will generate the field. Okay. All right, let's go back to my example of talking about this guy. So this guy is using a cable trying to drag a big box, right? So this guy he'll say, I apply force to box. The box also apply reaction force to me, right? So they cancel. I can never drag the box. So what is the problem in this statement? Anyone?
The forces don't cancel because one is applied on the box and the other is applied on the person.
Right. So we need to remember they are in different targets, right? This force applying F12 applying on the box, and this one applying to the person. And the box will move or not depending on all the forces applying to the box, not to the person. So it doesn't matter. If the box, there's only force on the box, will be the normal force and the gravity force and this force. So there are three forces acting on the box, and these two may cancel. Then this one will move the box and accelerate the box. So the point is that the understanding of Newton's third law is they are not acting on the same object, so they will never cancel. All right, so now we have a good understanding of Newton's three laws. Let's see how we can use them to solve problems. So before we go further, talk about the forces. The normal force, normally the forces, so here I list, not here. Let's talk about what is the normal force first. So what is normal force? Normal force. Does anyone know what is normal means here? That means it's general, or it's a...
It's the force that pushes up from the ground.
Yeah. So if you have a box, you have a ground, right? The ground push up, this is a normal force. How about you have a box, you push it into the wall? Where is the normal force here?
The normal force points out from the wall.
Okay, this is normal force. So normal means actually perpendicular. So the normal force is always perpendicular to the contact surface. Okay. I always hear some sound, but I don't know how to see the chat. So Not sure what the sound means yet. But anyway, so for example, if let's make a more complicated case. So if I have this is the ground, right? And there's a stick. And I push the stick along the stick direction, the length of the stick. So what is the normal force direction on this stick?
It points straight up from the ground, so it's
Right.
perpendicular to the ground.
It's perpendicular to the ground, because for this stick, its a contact is 1 point, but the surface here is flat. So basically, the normal force is always perpendicular to this contact. Sometimes we have other condition, like if two stick is connected by a pivot, then in this point-to-point of condition, there will be no contact, no normal force. It's harder to know the direction of the force in this case. But if we have a surface to surface or a point to surface, then it's easy for us to identify the direction. It's always perpendicular, because normal means perpendicular. So this is a normal force. So the simplest case is you have object on the ground. Then the object is not moving. That means the total force on the object is 0. But we know on the Earth, it always has a gravity, right? So what is the other force to balance this gravity? It will be the normal force from the table or the ground, which is equal to the gravity in magnitude, but opposite direction. So how about we have a box and on the ground, and we apply a force on the box. So now we always draw the force from the center of mass, okay? So if we have mg, then I apply a force on this point. That's it, just be F. So what is the normal force right now? Basically, we have to redraw it as there's mg. We assume these two are the same point, but we want to draw like this parallel so they can easily be distinguished, mg and f, right? So if we only have this gravity and this force, and if there's no other force, what is the result if we only have this force?
The box would accelerate downwards.
Right, because in this way, the total force will be mg plus f. So we'll have an acceleration, which is g plus f divided by the mass, right? Now, because this box is on the ground and not moving, which means what?
The net force is 0.
Right, because it's not moving, or it's moving with constant speed or velocity, that means the total force is 0. Because we know the sum of these two forces here, then we need another normal force, which will have to balance these two, okay? Another simple example is you have a box, you're pulling up with some force, and it still has gravity, it's still not moving. If this is the case, what is the normal force in this case? normal force, we'll use a N equal to what in this case? Anyone?
F minus mg.
F minus mg. What's the direction of this normal force?
It depends on how big F is.
Right. Okay, let's see. If F is greater than mg, right? The normal force will be, if you use this F minus mg, normal force will be positive. Is that right? So what direction should it be?
It should be negative, but I think the equation's wrong.
So the point is, the normal force is always pointing away from the surface, right?
Yeah.
Away from surface. So the normal force is always going up in this case. Then look, the up direction, we have a normal force and the force. The down direction is mg, so the normal force should be mg minus F. So if F is greater than mg, then we got a normal force that's negative. So is that possible we have a negative normal force?
No.
It's not possible because this force actually will lift up this box, right? Because normal force must be greater than 0. If the force cannot lift the box out of this surface, that means it's sticky. Then that's another force. We cannot call that a normal force. We have to call that, if there's a sticky things in here, right? And this force, which is greater than mg, then we have this is gravity is mg. Then we have these sticky things dragging this thing down. We'll have to call that a tension force. we usually don't call that a normal force. Normal force is basically the repel force from the compression. So if it's sticky, we can call this, we can think about there's a lot of small strings in here between these two. So that will be called the tension. Okay, so we know normal force now. So now let's talk about some other force. Usually when we have a string, right, we see a lot of strain in physics. A strain, we have two, for example, if we have a two-person, one is pulling to the left, one is pulling to the right, and the strain is something in between. In this case, we call the strain has a tension. And we define the tension to be F in this case, because it has force to the left and force to the right. And it has this tension F everywhere along this string. So we call this string has a tension F. So some people will ask why this is not 2F, because you have force to the left and you have force to the right. Is that T equals 2F? Let's see. This is basically involved what we call the free body analysis. We'll talk about this more later. So free body analysis means we find an object to study. So in here, in the string, If we treat the string as one object, it has a force to the left and a force to the right. Okay, good. A equals 0. The string is not moving, right? Usually in a problem, a string will be stated as massless string. So do you know why we want to state a massless string? If we have a massless string, and if we have a F1 on the left, F2 to the right, but F1 greater than F2, what happened in this? What happens if F1 is greater than F2?
The string would, well, if it had mass, it would accelerate towards the direction F1 is.
Right. If it had mass, it accelerates to the left. But if it's massless, what conclusion we can get if it's massless?
It can't really accelerate.
Because the summation of total force, right, will be F1 minus F2, which is greater than 0, but mass is 0. What is acceleration in this case? So we are dividing by 0. So sometimes we say divide by 0 means that has no meaning, right? It actually has meaning. Think about this. Let's draw a curve of force to mass, okay? For example, if let's not draw a force to mass. Let's draw acceleration to mass with a constant f, which means, for example, if we have a constant force acting on an object, right? If the mass is here, for example, we measured a point here. If mass is here, m1, the acceleration will be a1. Then, if mass is in the middle here, m1 divided by 2. So what is acceleration? What is the point we need to draw in this graph? What is acceleration when we have mass is half?
There's twice as much acceleration.
Right, there will be twice. So this is how we draw the curve, right? So I draw it to, the scale is not right. So let's draw it again here. For a constant f, our mass and acceleration relation will be something like this, right? Because the formula is A equals F divided by M. So the greater the mass, the smaller the A. But the smaller the M, the greater the A. So if you look at this limit, when the M, which means if M go to the limit of 0. How do I write that? Yeah, let's say just write something like this. If M go to infinity, we know that A will go to 0. Instead, another way, if M go to 0, which means acceleration will be infinity, right? So this is what we call a condition which is not possible, because if F1 greater than F2 and there's no mass, we'll have an infinite acceleration for the cable, for the string. So we call infinite A force strain, which is impossible. That means F1 has to equal to F2. So that's what the massless strain means. When you have a massless strain, the force on the both sides, left and right of the side of the strain, must be equal, right? Because in mass, what we call, because if this happens, the conclusion is not possible. So this cannot happen. So the massless strain is equal to F1 equals F2. Equivalent, they're equivalent. Okay, so that's why we can have this definition of tension, right? Because if we have a strain on left side and right side have a different force, how do we define the tension? Is this tension F1 or F2 or anything in between? We don't know. So for a massless strain, the left side and right side is the same. So we have the tension also to be same. F1 equals F2. So another way of thinking is, if we think about the strain at a bunch of molecule or elements together, right? If we have a force on the left and force on the right. So for the first element, if we think about the first element, this first element, there's a force to the left. Then the next element, element 2, must apply a force of F to the first element, right? Then for the second element, the first element apply a force of F, the third element apply a force of F. So you can see a strain is, if you think about strain is a lot of elements, then for each element, their force analysis is the same. Every element have a force to the left and force to the right. And they are the same magnitude F as what is applied to the left and right. So in this condition, we call the tension is same to F. Okay, for strain, the thing is, this tension must be greater or equal to 0. You cannot have a less than 0 tension, because a strain will turn into a loose strain, and there's no tension in here. But if this is the pole, it's a bit different. A pole is something you cannot stretch, but you also cannot compress. So for pole, we don't call it tension, because you can have a pole have both way F, or you can have both way push inside force. Okay, so another one is talk about is this is tension force. The other one we talk about is the spring force. Okay, it's 1 hour. Let's continue after 5-minute break. All right, welcome back. So we talk about, okay, let's go back to the spring force. So spring force basically is the Hooke's law, right? Most people should know. So a spring, if we stretch the spring, Okay, if we stretch a spring, this is a relaxed spring. When we stretch it to a delta x, the tension in this spring basically is something we call a constant times, we cannot use tension because we'll say this, so the spring can provide a stretch inside if there's an object here. But if we compress the spring with the delta x, then for the object here, the spring will provide a force of push. So this is the pull, and this is the push, equals k delta x. So anyone doesn't know the Hooke's law? If it F equals k delta x, right? So we'll see that later. So I already talked about what is the free body diagram, basically a free body analysis. So free body analysis, there's a few steps. The most important step actually is identify the object. So you can use one object, you can use multiple objects, and you are not limited to one object. So when you want to use multiple objects, you can actually draw a box around all the objects and treat it as a big object, okay? Then you identify all the forces acting on the object. Because this is not a 1D problem, so we have to choose our coordinates. We define our x and y. So this x and y doesn't need to be horizontal and vertical. It can be tilted, depends on the situation. Then why we need the coordinates? Because we want to turn those 2D problem into a 1D, into two 1D problem. So we resolve these forces into components in both directions. Then in both directions, we can find the sum of the force. Then we can find the acceleration in that direction. Then if there's two equations in two directions, we can solve the system equations to find what we want. Okay, so let's do some examples and you can see how this works. So the simple example I already said is a box on a ground, right? So let's do it again and see if everybody got it. So let's go around the class and make sure everybody know how to do a simple system, a free body analysis. So for a box on the ground, first we identify the object, right? Object is the box. Then we find how many forces on the box. Okay, Kevin, are you there? I cannot hear you. Can you try again? Leave your microphone on for a little longer.
How about, is this good?
Okay, voice a little low, but I can hear you. So, well, how many forces is acting on this box?
2.
Okay, 2. Which 2?
Gravity and normal force.
Okay, we have gravity and normal. So the thing here is we have only 2 in one direction, so we don't need the coordinates right now, right? Gravitation. Okay, so now let's make it a little complicated. if I applying a force to the left, so how many force now on working on this box?
4.
4? Which 4?
Friction, normal, gravity.
Okay, I haven't talked about if there is friction. So if there is friction, but let's talk about non-friction right now. There's a frictionless surface.
Okay.
If it's a frictionless surface,
3.
there's only 3, right? 3 forces. So how do you want to choose your coordinates in this case? Normal xy?
Yeah.
So normal xy. So how many force in x direction?
1.
Only 1 force in x direction. That is F. How many in y direction?
2.
2, which is N and mg, right? So now the sum of the force in x direction is just F. We have this m ax. The sum of the force in the y direction, because N is going up, mg is going down, so we use N minus mg. We're equal to may, right? So what is ay then here?
0.
So ay is 0 because we know there's no movement in the y direction. And this object is moving along the surface. Then what is ax?
It depends.
It depends on the f. So we basically solve this. This will be the simple answer for that. All right. Thank you, Kevin. So let's try another one. So if we have 2 boxes, M1 and M2. Okay, let me draw a line here. And we have a F, and they're on a frictionless surface. So I want to find the acceleration for these 2. So Ben, are you there? Okay, Ben is not available. How about Albert?
Hey.
Hi. So if we want to find acceleration for these 2, what is the object we are studying? Step 1. Find the object, right? So are we using M1 or M2 or together?
Together.
Yeah, so in that case, we can draw a big box, okay? So we treat them as one object. So let's study this one object. What is the total force?
F.
F. What is the total mass?
M1 plus M2.
M1 plus M2. So we can easily get acceleration is F divided by M1 plus M2, right? Okay, now we have more steps to do. How about if we want to find the tension in between these tension? How do we do that? If we want to find the tension between these 2 mass. So here, if we want to find tension, because tension is internal in this object, right? We cannot find the internal force if we study the whole two objects together. So now we have to we have to choose another object. So now, which object do you want to study if we want to find the tension?
M2.
Okay, let's study M2. Okay, let's study M2. So how many force is working on M2?
F.
We have the F to the right, and we have tension. Tension is to which direction?
To the left.
Tension is to the left. Pay attention is that the tension to M2 is to the left, but the tension to the M1 is to the right. Okay, so for different, that's the property of the tension for different object. You need to pay attention to which way this string is pulling you. So we have two. So now we have a total force equal to, if we choose the coordinate to be this, X and Y. So the total force is F minus T. The mass is Albert, what is the mass for this object?
M2.
M2. So what we get is A equal to F minus T divided by M2. So we have two unknowns here, right? We have A, which is unknown, and T is unknown. So how do we get the T if we have two unknowns?
You can get another equation.
Yeah, actually, we already solved A from here, right? So you see, to find the tension, we actually have two analyses. One is we study these two objects at one. Then we find acceleration. Then this acceleration can be applied here because they are the same. So now we already solved this acceleration, which is F divided by M1 plus M2. Now it's equal to F minus T divided by M2. So can we find the T now?
Yeah.
What is it?
Wait, do I solve it?
Let's solve together. So let's write again. We have F M1 plus M2, which this is acceleration, right? Equal to F minus T divided by M2. So can you solve T from here?
Cross multiply.
Okay, let me see if I got it right. Okay, cross multiply. So we got M2 F equal to M1 plus M2 F minus T, right? So we move this to the right. We got M1F. We move this to the left. We got M1 plus M2 T. So we can get T equal to M1 F M1 plus M2. Okay. So is there any other ways to solve this? So you see, when we have two mass, we try to use both as object to study, and we use M2 as objects to study. We haven't tried to use M1 as object to study, right? So let's try that to see if it's easier. So if we use M1 as the object to study, how many forces acting on M1?
T.
Only T, right? So we got T equals MA, M1A, which is the A we already know to be what is A we just found already? If we look at here, we already find A to be F divided by M1 plus M2. So it is F divided by M1 plus M2. Okay, see, we don't need to solve anything like this, right? We directly got this answer. So see, there's a multiple ways we can do the analysis. So be smart and find the best way of object. So basically, there's three objects to study. You can study M1, you can study M2, or you can study them together. But if you choose M2 and M1, you got two equations, and you can solve it. If you choose M2 and M1 plus M2, you got two equations. But the easiest one is you study M1 plus M2, then you study M1. Because that'll give you a direct answer. All right, thank you, Albert. So when we see the multiple, okay, let's do a similar example. If you have two objects, M1 and M2, and you are pushing using a force F. So how do we find the normal force between the M1 and M2? Alan, are you there?
Yeah.
Okay, so do you have any idea how to do this to find the normal force between M1 and M2? If there's a frictionless surface?
I'm not sure.
Okay, so okay, how many, first let's see how many different choice of object we can study.
2.
Which two?
M1 and M2.
Okay, we can choose M1, we can choose M2. Is there any other one we can choose, like we just did?
The tension. Oh, both of them together.
Yes, we can also choose to study them together, right? So we can also choose to M1 plus M2. Because you only need two equations, so you only need to choose two of these three. So which one you want to choose? Do you want to choose M1, M2, or this?
Both of them.
Both of them? Okay. Okay, if we choose both of them, what do we find? What's the equation when we choose both of them?
Force equals M1 plus M2 times acceleration.
Right. So now we got one equation from study this, right? Now we need another equation to find the normal force. So which one you want to choose? M1 or M2 here?
M2.
Okay, let's choose M2. So if you choose M2, what the equation you got? How many force? Let's study M2. How many forces acting on M2?
2.
Which two?
Like force. Just never mind. Just force.
What force?
Like the force acting on M1 and M2.
The thing is, the force is acting on M1, right?
Yeah.
So what force is acting on M2? So this force, see the contact point is on M1, right?
Oh,
So
yeah.
this force is not acting on M2. Only when you choose this M1, M2 as one object, then this F is working on them, right? So if you study M2 alone, how many forces working on M2? So look at M2. What object is in contact with M2?
M1.
M1 is contacting M2. So what is a force M1 provided to M2 called? If M1 is the source, M2 is the target. There's a force between their surface, right?
Yeah.
We talk about the force, what it's called when there's a force between two surfaces. And they are perpendicular to the surface.
Normal.
Right. So see, basically there's a normal force pushing M2 to the right, and there's a normal force pushing M1 to the left, right?
Mm-hmm.
So is there any other force working on M2?
No.
Actually there is the gravity
Gravity, yeah.
and this normal force, right?
Yeah.
But this normal force, this pair we can ignore, right? Because we know they'll cancel. So the total force is normal force, this one, is equal to so what is object we are studying?
M2.
M2 times what?
Acceleration.
Right. See, now you got two equations. Now can you get me what is normal force when we solve these two equations?
So like
so let's see which variable is known. So we talk about the F is known, right? F is known, M1 is known, M2 is known. A is unknown, M2 is known, N is unknown. So we have two equations and we have two variables. We just need to cancel A, right?
yeah.
So how do you cancel A?
So F times M2 over M1 plus M2.
Right. So it's pretty straightforward to solve this. So you can see these two, they have very similar answer. All right, thank you. Thank you, Alan.
You're welcome.
All right, see, this is some examples we talk about. There's a multiple object, and we have choices of solving them by choosing study one object or study them together. So this basically, if we study them all, it's redundant. Because if we see here, we study M1 plus M2, we got this equation. If we study M2, we got this equation. But if we study M1, we'll get an equation similar to this one here. But these three equations are redundant because you from two of the equations, you can get the third one. So we only need to study two of them. So if you look carefully, let's talk a little bit more about this example first. So you can see there's we have M1, we have M2, and there's a force. Then the normal force in between is M2, M1 plus M2, F. See, that means this is the partial of F. So if you look carefully, this M1 will have this force to the right, this normal force to the left. So the total force is actually F minus this N, which is M1 divided by M1 plus M2. F. Then for this M2, the total force is this normal force. So it's M2 divided by M1 plus M2F. You can see they all have, and the acceleration is just these forces, total forces divided by their mass. So you can see the A is F divided by M1 plus M2. Right? This A is same for M1 M2, and this acceleration times M1 will be the total force on M1. This acceleration times M2 will be total force on M2. And if you plus them together, it's just the total force. So you can see the force, the F, is distributed into these two mass proportionally to their mass. So they have the same acceleration. All right, let me see. So if you are not familiar with how to do the diagram, take a look at this slide. We identify the object, identify all the forces, choose their coordinates. So let's see an example of a two-dimensional force. Now, if we have a box, okay, and we have a force F1, and we have another force F2. This one has 30 degrees. This one is 45 degrees. Okay. And we know this is having an acceleration of 10 meters per second squared to the right. Assume, let's say, the mass is 1 kilogram. If this force, let me think, if this force is I cannot, I'm making up this problem, but I need to make sure the numbers are right. Let's get rid of this. Let's get rid of this acceleration first. So if we have, this has 10 Newton, we want to find what is F2. So acceleration is to the right. Okay. So anyone want to do this?
I can.
Okay, thank you, Claire. So let's start from our object, right? We have this one object. How many forces is acting on this object?
4.
4. Okay. I have to say that again. Yeah, this is a top view. Okay. Yeah. So that's the ground. Okay. So what is the 4 force we're talking about?
Gravity, normal force, F1 and F2.
Okay. So the F1 and F2. The gravity and the normal force we can ignore, right?
Yeah.
So we can draw them as one go into the paper and one go out the paper. Out of paper is the normal force. Into paper is gravity. So they are canceled.
Yeah.
Okay. So now we need to choose our coordinates. So do you want to choose the normal one like we usually do?
Yeah.
Okay, that's X and Y. Now, because all these are vectors, so we need to resolve them, right?
Yeah.
So we need to resolve f1x is
10 cosine 30 degrees.
the 10 cosine 30. Okay, let's leave the calculation later. f1y equals
10 sine 30 degrees.
10 sine 30 degrees. Then f2x is
F2 cosine 45 degrees.
okay. Then f2y is
F2 sine 45 degrees.
so now what is a is to the right means, which means a is in x direction, right?
Yeah.
So what we got if with the a is in x direction?
Basically, it's not accelerating in the y direction, so the net force in the y direction is 0.
Okay, so how do we write that?
10 sine 30 degrees.
Let me write this in y, okay? So 10 sine 30 plus
Plus F2 sine 45 degrees.
equals 0, right?
Yeah.
So, so if they are both positive, how is that possible with 0?
Because F2 goes in the opposite, well, in a different direction than F1.
Okay, so if we choose a coordinate like this, we'll need to write which sign as negative.
Okay.
So if we choose the up as a positive for y, right?
Yeah.
Any of these need to have a negative sign.
Then F2y
Right.
should be negative.
In that case, we'll have this as negative.
Yeah.
Then we can write this as negative.
Mhm.
Then it will be making sense, right? So we already got what is F2, right? It's just 10 sine 30 divided by sine 45. Okay, so now if I ask what is A, we need to continue to, how do we find A then?
You can use F1x and F2x.
Okay, so the A will be equal to F1x plus F2x divided by the M, right? So after here, you just plug in numbers and do the punch in the calculators. Okay, thank you, Claire. So this is a simple example of, there's a two forces acting on one object. And how do we resolve the forces into components in the XY direction? Because, if we don't do that, we will need to use the vector addition, right? If you do the vector addition, it's kind of awkward to do because you need to have this direction as a result direction, and it's harder to see how you draw this graph and solve it. It's doable, I think, but it's more convenient. We always try to turn the 2D or 3D vector operations into 2 or 3 1D problem, okay? Okay, let's say, so this is how the principle how to do the free body analysis. So there's a tricks we have to learn in the examples how you apply to do that, because sometimes it's harder to know which force is acting on which object. So I'll talk about this force. There's one more, it's called the friction. So let's talk about friction now. So what is a friction? There's two kinds of friction. One is called static friction. Which means there's something on the ground, right? Or any contact surface, and you apply a force, but it will not move. So why is it not moving? Because there's a friction here, right? You apply a force, there's a friction. So you increase your force. Let's say this is the force of you apply, and this is a friction. So before this value, whatever you apply to the block, it will not move. Because it's not move, that means the friction is same as your force. Until this value, then it will start to move, right? So this is what we call maximum static friction. We call that Fs. So Fs is, equal to the push force until the maximum value. We can say this Fx max. But how do we define this slope? For static friction, this slope is called mu s. Mu is the Greek letter. Okay, it's just like a u, but you add something on the left. Okay, so it's mu s. So mu s is the friction divided by the force, which means friction, you can always find the friction by using mu s times f. I mean, you have to use max friction. Before the max, the friction is always equal to the force, because if you only apply a little force, this object will not move to the left, right? Because the friction is only used to balance the force. It's similar to the normal force on the gravity. The normal force on the gravity depends on how much force you apply trying to lift. The more force you lift, the less the normal force. But the normal force itself will not help you lift this box. Okay, so this is called a static friction, and we have this coefficient called the static friction coefficient. There's another one, it's called a dynamic friction. That is when the object is moving. So moving. When it is moving, we have a force and we have a friction. This is D, this is S. So the dynamic friction is also in this graph, but it's a little different. When you have a force greater than the maximum static friction, there will be a line here. So basically the friction line will like this, going up, then going down a little bit, and then flat. So this flat line is friction, dynamic friction. And this line, this point here is the maximum static friction. So after, this is, you may have the experience, when you push something, you're trying to move something, at the beginning you need to give a push. It's harder than after it starts to move, right? When it starts to move, it's a little easier to keep it moving. So that's why this dynamic friction is a little less than the static friction. But of course, a lot of times we'll just treat them as the same. If that is the case, the problem we'll mention that we only have one coefficient. So we have this mu d equal to the friction divided by F. But remember, this is only when this object is moving. And usually the mu s is greater than mu d. But very often we treat them the same, okay? We just use mu when treat them same as same, okay? Okay, so a simple example is that if you have 1 kilogram object and mu s is 0.2, mu d is 0.18. So what is the force you need to push to make it move? And then what is the force to keep it moving? Keep it moving. So anyone? If you apply a force this way. Jocelyn. Jocelyn, are you there? Okay, Tracy, are you there?
Yeah.
All right, so I give you two coefficients of friction, right? So what is the force to make it start to move? Or let's say start moving. So do you have any idea how to do this?
No.
Okay, so as we talk about, because there's a friction, when you increase the force, the friction will balance the force, right? So it's not moving. But when you increase your force until it reaches the maximum static friction, when the force is over that point, it will start to move. So what is the maximum static friction? Oh, I think I missed something. I'm sorry. No, this is wrong. I talked it wrong. This is not F. So the friction is because the normal force. I'm sorry for this confusion. So this is the normal force. So because when the block is on the ground, they have a normal force in between, right? because you know the harder you compress something to the ground, the harder it is to move it, right? So the friction is depending on the normal force of the surface. So this friction is mu n, depends on it's static or dynamic. So now I'll go back to here. What is the normal force when you place a 1 kilogram box on here? If it is 1 kilogram, what is the normal force? Hi, Tracy.
I don't know.
Oh, you don't know the normal force? Okay. How about for a kilogram box, what is the gravity of acting on a 1 kilogram box? So you don't know how to find the gravity when you have a mass, right? So the thing is, how do I say that? Gravity is, yeah, let's restate that. Gravity. So everything on Earth will feel a gravity, right? And this force will be proportional to the mass of this object. So on Earth, everything, we have this on the ground, on the surface of Earth, we have this gravitational acceleration, 9.8 meter per second squared. So if you have a mass of 1 kilogram, what do you think the gravity is acting on this object? So if you drop a box of 1 kilogram, it will have acceleration of 9.8 meter per second squared. Right, Tracy?
Yeah.
So if the mass of this box is 1 kilogram, what is the total force acting on this box?
Would it be 9.8 newtons?
Yes. So the force is called the gravity force. Let's say Fg, gravitational force, with the mg, which is 9.8 Newton. But Newton is actually the same as kilogram meter per second squared, because this is just a SI unit. So this is same as Newton. Okay, but Newton in another way of writing will be kilogram times meter divided by second squared. Okay, so which means everything on Earth's surface will have Earth will have a gravity working on it, acting on it, which equal to mg. So anything on the surface of mass, if they are not dropping, here we talk about a free fall, right? A free fall because this box has the acceleration of 9.8, which because of the mass, we know there's a force acting on it. But if this box is not dropping on the surface of the Earth, then we know it still have this gravitational force acting on it. But what is the other force that balance this gravitational force?
A normal force.
That's a normal force, right? So what is the magnitude of this normal force in this case?
9.8 newtons.
Right, it's the same as the gravitational force is 9.8 Newton. This is 9.8 Newton, right? So when we talk about friction, the friction is, okay, the friction is the friction coefficient, this one, the mu, we call it mu, is a Greek letter, times the normal force. So how do we find the friction between any surface? It depends on the normal force. So even we have something, you know, if it's like this, if we push a force, we push a block into the wall, so it's not dropping. Then in this x direction, right? Because there's no gravity in the x direction, the normal force will be to the left. It'll balance this force is equal to F, right? Then the friction will be the normal force times the coefficient. So in this case, if we know the maximum, the mu s is 0.2, that means the maximum static friction is the mu s times n. So what is it?
1.96.
Okay, yeah, it's 1.96 Newton. So the maximum force. So that's what I asked. What is the force to make it to start moving? So the difference of this static and the dynamic friction is when the box starts to move, it doesn't have that much of friction anymore. So it only have a little less friction. So what is the force that keep it moving? Because when it, okay, let's look at the case. When this box is moving with velocity v, right? If it's a constant, then the total force on the box is what? Tracy?
Can you repeat the question?
Okay, is that if the box is moving with a constant velocity, what is the total force working on this box? So think about what is the Newton's first law or second law? A constant velocity means A equals what? Acceleration of zero, right? Yeah, because the acceleration is the slope of the velocity. So when we have a flat velocity, the acceleration is zero. Then the total force is what?
Also 0.
Yeah, so that means total force is zero. We already know that normal force and the gravity will balance out. They are zero in the y direction. Then in the x direction, we'll have the friction and this force. They are also balanced out. So the force will equal to friction, which equal to the friction coefficient, dynamic friction coefficient, times the normal force, right? The normal force is same as the gravity, so we already calculate that. So this is 0.18. The normal force is 9.8 Newton, right? So what is the force required to keep this box moving?
1.764.
Yeah, but we just keep 2 digits, right? Right.
1.8.
Yeah, it's about 1.8. So that's the question. So if you are not familiar with the friction, the concept of friction, you know, and maybe we can do a little more examples or read book about friction. Okay. All right, thank you, Tracy. So it looks like I'm running out of time, but let me see. So we already talked about the example of pulling box, pulling toolbox, a pulley. So if you don't know what the pulley is, this is the pulley. So the pulley is a wheel, you know, you can pull a string across it. So in a way, let me try to wrap up in 5 minutes, okay? So a pulley is something, actually you can turn a string. So if this is a pulley and this is a string, so this string go around the pulley, then the tension can be turned around like this. So if we have something M and another thing M here, they will balance. So this is very likely the tension working on this M is going up. This tension going up also. So the pulley is actually, you know, usually we have talk about string. We talk about a force to the left and force to the right. They're all same as the tension of the string, right? The pulley is just something that bend this middle part, make it can be curved like that. So you still have this tension in the string to be same as T everywhere. Then the force is same to tension, the force is same to tension, something like this. So when you have two objects on here, you can do the analysis. If you look at the left side, you have the gravity, you have the tension. On the right side, you have gravity, and you also have tension. Then you have two equations. But if they have different mass, then the tension has to be same because they are connected. As we talk about, a connected string, a massless string can only have the same tension everywhere. So here they will have acceleration up. If M1 is greater than M2, then if you study the M1, you have M1G greater than the tension. So you have M1G minus tension is M1's acceleration. But because they are connected by strings, so the acceleration of the left one will be same as acceleration of the right one, but in a different direction. So in the right side, we have tension minus M2G is same as M2A. So here we have the tension and acceleration as unknown, but we have two equations. So we'll be able to solve the acceleration and the tension in these pulley problems. The last one will be a slope. So when we have something on the slope, we'll have to choose the coordinates along the slope. This will be X, and this will be Y. Then we have the gravity, we will resolve the gravity into X and Y. In the Y direction, the gravity in the Y direction will be mg cosine theta, if this is the theta. And the gravity on the X direction will be mg sine theta. So if you study this object, you'll see there's only, if there's no friction on the slope, you'll see there's only two force, gravity and the normal force. Then this y component of the gravity will cancel the normal force. So the normal force, it will be mg cosine theta because they cancel each other. And in the x direction, we'll have the force of mg sine theta, which gives us acceleration along the x-axis of g sine theta. All right, so I'll stop here. If we have, we'll have more time to explain this next class. Thank you very much, guys. This is a homework. So try to do this online practice. It won't take you very long time. All right. See you guys next time.
Thank you.
Bye.
Thank you. Thank you.
Thank you.